So how you guys doing today?
Good.
Good. It's a Monday, right? Yeah. So let's start the week here today. So I don't know if you guys watched the video or attend the Friday lecture. We've been talking about the nomenclature of arcane. Arcane. Yeah. So we try to name the four main parts of the organic compounds: locus, duplex, base, and surface. So whenever we try to do this, first thing what you need to do is try to find out the longest possible carbon-carbon chain. Okay. So if this is the case, we actually have some question over here. So if you have this type of linear organic compounds, you just count the carbon chain. There's a 5. So this base becomes pent. Means 5 carbons over here. And then suffix just the ane, meaning it's all in single bond. And there's no additional groups here and here, so it's just going to be pentene. Okay. And then we add if we have some additional groups attached to maybe here, so we put maybe CH3 over here. Then we consider this additional group as R cubed. And what you just need to do is try to count the numbers of carbon here, which is just 1. So it's math. And then instead of we putting A and E, we're gonna put YL. So it will be methyl. Okay. So here's the methyl. And then now we have a prefix over there. We find our prefix additional group. We just try to find the locant for this one by just count the carbons from either left to the right or right to the left. And in this case, I'm going to count the carbon from left to the right, because if I count the carbon from left to the right, it will give you 2 carbon. It will have additional group. If you do the other way, actually the number 4 carbon will have a group either way. It's fine. But whenever you have a 2 choice, either carbon 2 or carbon 4 will have this group. We always go with the lower number. So this is why at this time we're going to count the carbon from left to the right. So you can have a lower number, which is 2, which will be a locant. This is indicating where your prefix are. So the 2 methyl pentene. So you may ask, then how about we have a methyl group in the middle, right? So either way, you count the left to the right, right to the left. It will be still 3, same, right? So in that case, you don't have to worry about which carbon you need to count first. So you give the same number anyway, okay? So in this case, don't worry. Okay. And then if we have maybe more than 1, okay? More than 1. So maybe we have a 2 methyl group over here. In this case, you can count the carbon 1, 2, 3, 4, 5. It's still 2 and 4. 1, 2, 3, 4, 5. Still 2 and 4, but the other way. So the number of combinations is still the same. So now the locant is just going to be 2 and 4, 2, comma, and 4. Okay? Because now you have a 2 additional group, so you have to put also 2 locant numbers there for each. Okay, it's 2, comma, and 4. And just one more thing you have to do is there are 2 methyl group here, so we're gonna put di. Okay, di. So the full name of this compound will be 4,4 dimethyl pentane. Okay, so this is a kind of what we did on Friday. Yeah, Friday. So then, how about we have all the more compounds, more complicated. Okay? So maybe you can try to get the okay. So the octane, right? Because 8 carbons, the oct, all single bond octane. So in this case, maybe we have one methyl group here, and we have 2 carbons attached to this one, not one. So this will be CH3. This is CH2. 2. Okay. So try to get this one. Okay. So in this case, I'm going to count the carbon from left to the right, because if you count from the right to the left, we'll give you 1, 2, 3, 4, 5, and 6. I'm sorry, 5 and 7. But if you count the carbon from here, it will be 2 and 4. Okay? So 2 and 4 is better than 5 and 7, right? So we're going to go with the 2 and 4. But this is what? Once again, methyl group here. In this case, now we have 2, right? So 2 means what? F. Okay? You know that if there's some nomenclature to do. So it'll be 2. So, but once again, this is additional group, so it'll be ethyl group over here. So this will be about number 4. Okay, you can put it in number 4 over here. Okay, so if in this case you're going to have 2 methyl and 4 ethyl or ethyl, P1. 2 groups are here. But I don't know if you guys remember, I briefly mentioned at the end of the Friday lecture that I'm going to order those 2 different groups in alphabetical order. So what I mean by that is, if you look at the methyl group here, it has 2 over there, right? 2. And ethyl group has E. Okay. So now you know, oh, E comes first, then M, right? In alphabetical order, right? A, B, C, D, E, F, C, right? So then you can put this. You can put this first. So it's not going to be 2 methyl, 4 ethyl octane. It is actually going to be 4 ethyl first and 2 methyl and octane. Because the E comes first, then M. So I'm gonna write 4 ethyl and 2 methyl octane. Okay, perfect. So the this is another thing. So maybe if I give you, okay, let me give you. Okay. So I made a now. They came, right? They came. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So, okay. So if we have now 3, okay, here instead of here 3, okay. So in this case, this is going to be prop, but we're gonna put what? YN, right? So propyl. Okay. So we count this one again, 2, 3, 5 in here, and this is the 3 methyl here, methyl, and this is a 5 propyl. It's just same because the prop means there's 3, but I just put the YL instead of ANE because it's an alkyl group, additional group to your base. Okay. So in this case. Can you guys guess which would come first, M or P? M, right? Yeah. So in this case, you're actually going to put this methyl group first. So it will be 3 methyl, 5 propyl, DK. Okay. So it's the same, butyl, pentyl, so on. whenever you have a numbers of carbon based on that the base name, and then put the YL to make it alkyl group. You can do this, but make sure you just need to order them in alphabetical order. Okay. Makes sense, right? Okay, perfect. All right, so there's just one more thing, or actually a couple more things I want to tell you. So if we make this one, I might give you this one, okay? This one over here. And then maybe this is now 3. You have a 3, okay? You have a 3. And then in this case, we have a 2 methyl group on the same position. So it'll be 3, 3 dimethyl. Right? Because now it has 2. So that's why I put di. If there's 3, tri, 4, tetra, so on. Okay? But just the meaning how many same groups are where in those local with it here. And you also have 5 ethyl group over here. Okay. So in this case, if you count the D here, dimethyl D here, if you count the D as an alphabetical order, you're gonna write 3, 3 dimethyl and 5 ethyl. That came right. But we put it in this way because we count the di and D as alphabetical order, but this is wrong. Okay, so whenever you do di, tri, tetra, penta, hexa, so on, those ones are not counted for alphabetical order. So you still count this as M, not D. Okay, so same thing for tri, not T, but still M. So everything is that way. So whenever you have some additional name for the indicator how many of those, like di, tri, tetra, and hexa, don't mind it for alphabetical order, but just what it really was, which is methyl group there. So it will be still 5 ethyl 3,3 dash dimethyl. Okay, so it will be still ethyl first. Okay. Yeah. Okay. So once again, D does not count by alphabetical order. Just M still. Okay. Makes sense, right? Bit confusing is good, right? So it just this one doesn't count over here. So if that is the case, I'll give you a little more. I think 1 or 2, and then we can finally almost done with the nomenclature of alkane. Most of the case. Okay, so if that is the case, how about we have some groups over here? So how about we have groups like a branch, like a Berkeley group over here. Instead of linear, we have a Berkeley group here. So in this case, it's a bit more complicated, but it's still the same work. The only thing you have to do additionally is to try to make this one as the separated groups. Meaning, in here, you're gonna just try to find the longest carbon chain again. So if it's not linear, what you can do is you just separate them from here at the moment. Just forget about the base here. Just try to focus on the group first. In this case, you're going to have a carbon that's starting from the middle. So longest possible chain from the middle is 1, 2. If you go the other way, it's the same, 1, 2, right? So this is as you're like another separate group. So maybe I can put this is the longest carbon chain from the middle is just 2. So I'm gonna put ethane, okay? Just ethane over here. And then if this is ethane, you can consider this one as a additional alkyl group to this one, which is located at 1, 2, okay? Because I'm not gonna count it from 1, 2, because it will make a 2 for this one, but 1 is lower than this one. So I'm gonna put 1, and this is 1 carbon, methyl ethane, okay? So we just name this one first, okay? So we're good. We're good, okay? We're good. So now we know what the name is for because it's separated. But the thing is still is the additional group to the bigger base, okay? So in this case, you're just gonna change this one to white again, okay? So you make your the bulky groups as just the additional group to the bigger base, okay? So now you have 5 over here, okay? And then 1 methyl, okay? And then this is 3 methyl group still. Let me actually put this in the this 5. Yeah, just keep it there. I'm thinking. Okay, so we still count them as M, but I put this one first because it has a lower locus than 3. So even though this whole thing has a locus number 5, the one in here is still lower than 3. So we put this one first. Okay. Does it make sense? Somehow? Okay, let's check. So we have a better name for this one. This is kind of confusing. I just want you to know how to do this. But if you want to have a better name for it, this is something which you can do. So we can also do it this way. But if you look at those numbers of a carbon here, there are 3, right? So we can just start with the pro. Okay, propyl. Okay. We start from the propyl here, but this is not linear because we're not meaning like 1, 2, 3, but it's 1, 2, 3. It's a more bulkier than linear. So in this case, if you have only 1 carbon sticking out from the other carbons in the whole groups, you can put isopropyl. Okay. So isopropyl means you have in total 3 carbons, but there will be 1 carbon sticking out from the other carbon chain. That's what iso means. So you can also put this in the 5 isopropyl and 3 methyl. Makes sense, right? So the isopropyl or 1-methyl, it's the same thing actually. But this is a much easier way to put because this is you only need to count the total numbers of carbon first, but it's not linear. It's not just like 1, 2, 3, but it's 1 sticking out from the other carbon chain. So we kind of name this isopropyl here. The thing is whenever you do this one, whenever you put the iso, we normally put this in the capital I, and you count this I as a alphabetical order. So this is why this is a propyl. So if it's just the regular propyl, it could have been actually later than this one because the P comes next later than M, right? But I put the iso first because now we count I for alphabetical order. So it's different from what we did for di, tri, tetra. The isopropyl is the I, not P. Because the iso we normally put in the capital letter, and I comes first, then M. So this is why I put the 5-isopropyl 3-methyl decane instead of 3-methyl 5-isopropyl decane. So I didn't count this as P, but I for alphabetical order. Kind of makes sense, right? It's just getting there. Okay. So I want you to also remember this one. I'm sorry, I'm gonna make a little bit more thing to memorize. Okay. So how about we have more molecular groups over here. Let's start with this one actually first. So if you have this one over here, okay, that means you have in total 1, 2, 3, 4. Okay, 1, 2, 3, 4. So it's a but. But this is our key group later, so I'm gonna make it butyl. That's okay. But the thing is this is the carbon we can start with, and it has neighboring with the 2 carbons. Okay, 2 carbons over here. So this is what we call. So we separate from here. Don't worry about the base. Okay, at the moment. We have this carbon that is neighboring with the 2 other carbons over here, and we call this secondary because it's neighboring with the 2 carbons over there. So this is the secondary butyl. Okay. So in this case, we're gonna put SEC only. And we're not going to put the secondary whole word, but just the 3 syllables, SEC, in italic form. So you see the letters are kind of lean on to the right. So the reason why we put just not in the regular font, but the italic size, because when you put this in the nomenclature, you don't count S as alphabetical order, but just B. So this is different from isopropyl. So isopropyl, you count the I for your alphabetical order. So we change the order, right? It comes first, then the methyl group here. But when you do the secondary butyl, so we get the SEC butyl, we don't count S, but B. That's what we're gonna specify. We're gonna make this not so important for the alphabetic order, so we italicize those 3 letters. Okay? So that means this 5, B comes first in M, right? So we're gonna write this one first, obviously. So be 5, italicize SEC, okay? Butyl, and 3, methyl, decane. So we're gonna do this in this way because it's a secondary. Okay? Make sense? Okay. So how about we have another form of butyl that has even more molecule. Okay, looks like this. So same here. It still has 4 carbons. It's still butyl. But obviously it's different from the one we just did, okay? So not just 1, but 3, not 2 or 3, but now it's a 3. So this is now, forget about the base for the moment. It has the 3 carbons around it. So it's not primary or secondary, but tertiary. So we're gonna put T-E-R-T. So we're not gonna write all the words for tertiary, but just 4. So it'll be T-E-R-T. Okay. And same thing, this is the same as for your secondary butyl. We're gonna write this one in the italicized. So this is also does not count for alphabetic order. It's still B again. Okay. So if this is the case, we're not gonna put this in the later than M because it's T. No, we don't count the calculate as a T, but still B. So it comes first. It doesn't come later than M. I know T comes later than M, but we count this as B, not T. That's why we're putting this one in here. And that is why we kind of italicize this third and secondary, so people will know, oh, why it comes first in the nomenclature of the compound. Yeah.
Is there a hyphen between the tert and?
Yeah, you can definitely do it. Yes. You can definitely do this. But to be honest, if you get this number name right, if you make a one mistake by just hyphening it, I will not put much of point deduction there. But I just want you to know.
Is it supposed to be together? Is it supposed to be like one word?
One word.
Tert and you. Like, is there supposed to be a hyphen there? Or is there not?
Yeah, you can. Yeah, hyphen there. Yeah, top it.
Okay.
So, but once again, if you can get this name right, and make sure you guys have SEC, TRUT, not, just do B. But the only exception you can have for is the isopropyl. Alrighty, makes sense, right? Okay, perfect. Okay, so that's pretty much it. That's it for the nomenclature. Alright, so if the next part of the chapter 3 is about the confirmation. Okay. So confirmation is about the rotation of the single bond. Because I'll tell you once more later, the double bond and triple bond cannot rotate. So only if you did a single bond, it can freely rotate to left or right in different angles and so forth. So if it makes any change of the structure by just rotating the single bond, you have some lot of different types of the conformers, meaning different structure by conformation. So if I give you one example as the ethane, okay? So if you look at the ethane over here, of course there will be the 2 carbons over there, right? But each carbon should have three hydrogen, because there's one single bond between these 2 carbons. But this all will fill with the 3 hydrogen, so it can make all single bonded over there. Okay. But the thing is, it's kind of hard to look at it on the 2D. But if I do my best, this is what we call Soho representation, meaning you kind of look this one from the top down, but 45 degree to the side. So I kind of make sense. If you have this one, so this will be about this degree, right? This is a tetrahedral structure, right? And then the one on the, so you can think this, you're looking at this one like in this way. Okay? So that makes, this is carbon on the back, like the back side of this board. And maybe this is on the front. Then it has like a bond angle to carbon, hydrogen here and here, and all here and here and here. Okay? So let me actually do this one the other way maybe. Okay? So it has here and here, here and here and here. Okay? So if you put this, if that is the case, this is kind of okay for us to see how does the carbon and hydrogen are bonded to those carbons front and back somehow. But we have a better way to put this in the 2D picture, as we call Newman projection. So we have this front carbon here at the point, okay? And then we're gonna put this 3 bonds from this carbon. We put the hydrogen over there. And then the carbon on the back, we actually represent as like a bigger circle. So we actually looking at this carbon in right confronting way. So this is the front carbon, the back is right there. But if you're putting all 2 in the dots, there's only 1 dot, so you cannot represent it different way in the 2D. So we make this back carbon like a circle. So this is the front carbon, this is the carbon on the back. Okay, so in that case, you have this one, and this one, and this one. Okay, so you kind of see this on. Do you see this? What I'm drawing here? Okay, good. So this is the front carbon here. So we can say there are certain like angles between the carbon hydrogen bond from the front carbon, the carbon on the back, and like here. See, I know we is all 109.5 degree in the 3D, but in the 2D will be all by about 60. When you put it, when you look at from the like a front to the back. So this will be 60, 60, 60, 60, 60, 60 in this picture, not on the actual bond angle, but here. So if that is the case, we're gonna have this form here, okay? We can have another form here. It looks like this. Like this. Okay? So you see, they're not nicely all spread out in the almost similar like the bond angles, but this one is just what almost aligned with each carbon and hydrogen bond. The front and the back are almost parallel to each other, right? This is okay. So we kind of worry about this one sometimes, but this because this will give us a bit of a different in energy status. So this is stable, or you can say more stable than something, which is this one. So this is less stable or unstable. This is less stable. Okay, because the whenever you have this one, you have those hydrogens are kind of aligned in the same angle, same like a direction over here. So they're going to experience such type of discomfort, because if you look at this one over here, they're all well nicely kind of spread out in the 3D space. So there are not much of the energy required to sustain this form. But in here, you have a kind of like a bond in the front and the back kind of overlap on the same side, right? So this is why this is kind of less stable, a little bit more unstable than this one, because of the spacing problem. So if that is the case, we're gonna distinguish these two by naming this one as a staggered conformation. And this one is like a eclipse. So it's eclipsed conformation. Okay, because it's just literally eclipsed over here. So so think about it. this is stable. We call this staggered conformation because it's kind of staggered nicely on the nice other way. But this is eclipse, so it's kind of experienced some discomfort than the one of this one. So we call this eclipse the conformation here. So if you think about in nature, those single bonds in this organic compound will rotate, right? Rotate and rotate. But somehow, if this one wants to, if this one compound get into the eclipsed conformation, they wants to be stable, right? So they try to rotate. Once they get to the eclipse conformation by accident or by chance, where there's certain energy, when they get to this conformation, this naturally, thermodynamically, they want to go back to the more stable form automatically. So that is why this will have a rotate, right? So we call this much of the energy discomfort to be in the stable form torsional strain. So torsional means it's rotating, but the strain is like a hindrance, like a force. So they want to, when they get to the eclipse conformation, they go to this form. So they need to have certain way to express the force, and that is about 4 kilojoule per mole. Okay? So this is what we call torsional strain. Once they get into the unstable form, they want to go back to the stable form. They need to experience certain type of strain by rotating. So we call this torsional strain. Kind of makes sense. Oh, really? Oh, I thought that was kind of hard to. Anyway, so that's really great. So obviously, do you know why this wants to go back in this one, right? Because it's the discomfort they want to avoid, so they can be more stable. So I'll give you one more example, and hopefully I can finish this up by Wednesday. Then probably we have some room for the chapter 4. But if that is the case, let's look at the propane. Okay. So propane is looks like this. Okay. Okay. So in this case, we can look it up, and also in Newman projection here. So, but we're gonna either put this in these two or these two only. So we can either look at it here or look at it here. It's up to you. But the thing is, if you look it up here, this carbon will have 2 hydrogen, 1 methyl group. This has 3 hydrogen over here. So if you look at the first front carbon that has a methyl group over here, okay. The other one will have only 3 hydrogen. Okay, so this is on the back, this is in front. You're looking at it here or here, doesn't matter. Okay, so if that is the case, you can also say this one is what? Staggered conformation, right? Because it's kind of nicely evenly spread out in the uniform bond angle to each other. But if we change this one to again, in the eclipse conformation. Okay. Okay. This will be still same 4 kilojoule per mole. 4 kilojoule per mole. Okay. But this one will be 6. So do you see? They experiencing some discomfort by 4 kilojoule per mole here and here, but this is slightly higher than 4 because the methyl group is bigger than hydrogen. So because of its size, it has these two competing for certain room over there, but this one is more competitive space competition because the methyl group is bigger. So the amount of the discomfort they experiencing between methyl group and hydrogen is bigger than two small hydrogen. That's why it has a slightly higher number for the strain over here. So if you look at this one here, it's not just about the angle, eclipse conformation, but also because of the is what? Size, right? Size matter here. So if that is the some kind of a hindrance, the force generated by because of its size, we call that static strain. Okay, so this is why it's even more discomforting for those two. So on the top of the torsional strain, they're also experiencing the steric strain, which means if it's bulkier or bigger, even those discomfort will be even higher for those two groups. Okay. I'll stop here.